So last time we started talking about the Riemann normal coordinates. So Riemann normal coordinates. And in physics language, these are also called the locally inertial coordinates. Well, the idea is that any kind of space-time, if it's curved or not, first of all, we haven't really quantified how can we decide if some space is curved or not. But one thing we settled on, we agreed that if a coordinate system exists where your metric takes the platform, Minkowski or the Euclidean then exists where metric takes this form, then this is just a flat space time, and we know that if we change coordinates, if we go to some complicated coordinate system, this metric may look very complicated. We may end up with some Christoffel, with some connection coefficients, non-zero connection coefficients, but still we know that it's a flat metric. So if we are given a general coordinate system and we are given a metric in those coordinate system, how do we decide that if it's a flat space or not? If it's curved, how do we decide that there is curvature? So those kinds of questions we want to address. And in doing that, there's one very extremely important step, that we can always create some coordinates which are locally flat. What does that mean? We can always find a coordinate system so that at one point, because you know that the metric changes from point to point, so you will always be able to find coordinate system where at one particular point, if you plug in that value of the point, your metric, the metric takes the flat Euclidean form, Euclidean or Minkowski, whichever space you are in, the flat Euclidean form in that coordinate system. So this is extremely important because this connects directly with how we define physics in curved space-time. So we know that we have to describe gravity. Well, we have argued that we have to describe gravity using some kind of curved space-time. And how do we do it? How do we translate physics into this curved space-time? This statement is the connection which connects physics to a space-time geometry. So we have to study this in detail, and actually we should be worried that are there any curved spaces at all, because the way we have set up, we don't know. Is it possible? So you can ask this question, are all metrics Can all matrix be equivalent to the flat matrix in an appropriate system, in an appropriate coordinate system? Because we know that just by change of coordinates, I can change my flat metric into a funny metric, having non-trivial connection coefficients. So could it be that if you give me some arbitrary connection coefficients, and I can just find a new coordinate system where these this connection coefficients vanish, and the metric takes, that would mean that the metric takes the flat form. So that would mean that all this machinery I'm setting up is completely empty. All the spaces are just flat in some sense. So this is an important question to answer. And when we construct this, we will answer this as well. And actually, there's more, that not only this part is true, this is true, but also well, let me answer this question over here. This will not be true. And this point, that you can do it only at a point in general, is extremely important. You can do it at a point, but if you do it at one point, then the metric will not be flat at other points in this coordinate system. And in general, you will not be able to find a coordinate system where the metric everywhere takes the Euclidean form. Also, not only you will be able to put the metric in the Euclidean form at a point, the first derivative of the metric is also zero in an appropriate coordinate system. At a point, again, this is very important. You can arrange things so that at one point the metric takes the Euclidean form, and also its first derivative is zero. But second derivative cannot be arranged to be zero. And these second derivatives then capture the deviation from flatness. And the second derivatives are which construct for us something which we can call the curvature. So the proof of these statements is important because it gives us an idea that what's going on. And the proof is tedious but kind of simple. Proof is merely Taylor series with counting arguments. So let's construct the proof. So suppose we have some coordinate system, a given coordinate system. So we have marked our space with these coordinates. We have a given coordinate system, and let's call it prime coordinates. So I'm just for extra clarity, I'm putting on the coordinate a tilde, and I'm also on the components I'm putting on the indices I'm putting a dash in these prime coordinates. So we are given this, and we are looking for a new coordinate system. Its system x mu. So the new one which we are looking for is unprimed, where we are actually hoping to have g mu nu in this unprimed is just the flat eta mu nu or delta mu nu, which we were also writing as 1 mu nu. So g mu dash nu dash goes to, under the coordinate transformation, to the flat metric. And to start with, I'm hoping that I can do it. I can do it everywhere, not at a point, but everywhere. And this would be, in the end, we know that this is going to happen if the space-time is flat. But just to start with, I just suppose that I'm trying to construct something like this. So I'm constructing new coordinates to the Taylor expansion. Define the new coordinates, and we are only doing it in the paths, so not much technical difficulties we have to worry about. Just in a small region, as long as it's not a point, we are trying to construct it. So let me just write down Taylor expansion. Just as a reminder that if I have a multiple coordinates of a function and I can expand it at a point, so I'm expanding around a point P whose coordinates are x mu naught. So this is simply the Taylor expansion plus I will have things like these. There will be a half at this point, where x naught are the coordinates of the point around which you are expanding. So I am just merely now going to apply this to coordinate change. Apply this to you have this formula that you can write one coordinate in terms of the other. And so I think of this as a function of these and just apply this. So then I have x mu dash naught plus, well, let me, yeah, x alpha. So for each mu dash, I'm writing it. And each x mu dash depends on all of these coordinates, unprimed mu's. So this is the first term, and the second term would be x beta naught, and the double derivative and so on. So you can see that still the summation convention is working perfectly fine. So similarly, we can expand this metric components. They were the metric components given in terms of the prime coordinates, but the prime coordinate formulas are functions of the unprimed. I can think of them as functions of the unprimed as well. So thinking its dependence on the unprimed, I expand it. Thinking of its dependence on the unprimed coordinates. So then I will get these guys at point P is just the Taylor expansion. At P, and so the one thing to notice over here is that over here, these are just set of numbers. These are not functions anymore because I have evaluated them. Similarly, these are a set of numbers. These derivatives evaluated at points. All functional dependence is Taylor expanded. Similarly over here. Similarly in this formula. Now we use this Taylor expansion in the change of coordinate formula for the metric tensor. So our change of coordinates formula is, so use this in change of coordinates for the metric. So what's the idea? The idea is that you have this formula for the metric tensor that when I go from primed to unprimed, that's the formula which is obeyed. So I forced it that I just say that I'm doing this coordinate transformation, and as a result, I get the flat. And I'm looking for those coordinate transformation which will take me to flat. So I'm constructing the new coordinates which take me to the flat. And how do I construct? So construct the coordinates that convert the metric components to the Minkowskian form. And how do I construct? Construct using the Taylor expansion. So in other words, I'm looking for that relationship, those coordinates over here, those coordinates, which I'm going to define through this Taylor expansion by giving these Taylor expansion coefficients. And I'm going to adjust these coefficients so that I do get a flat form. Well, the metric is there. So whatever the metric is, that it is. But I'm doing a coordinate transformation so that it looks like this or this, whatever your signature is. So you just put the expansion, the Taylor expansion, in equation 1 and compare term by term of equal power of these guys where we are expanding. So what do you get at the 0th order? So, well, let me first, to construct this, first let me write this equation, because I will have to put those again and again. I take these defining relations. In over here, I have to compute these derivatives. So I compute just these derivatives from my defining relation. So I'm doing dx mu dash over here over dx alpha, this kind of thing. So when I do that, the first term is a constant. This is constant, this drops out. Over here, I will have dx alpha. Well, this is alpha is a summed index, so I should really change it to gamma. Over here, gamma over here, and then take a derivative with respect to alpha. I'll have a delta of Kronecker delta of alpha and gamma, which will change this alpha to gamma, and so and I will have another derivative written over here. So it will just change this alpha to gamma, but I can just keep it alpha because if I'm deriving with respect to alpha. In the next one, I will again get one time I will differentiate the first term, and the next time I will differentiate the next term. So let's just start writing and it should be clear. It's just that when I'll be writing, you won't be able to see like we do it on the board. But in any case, let me just start writing. Hopefully it will be clear. So I do this. In the first term, constant term drops out. In the second term, I get just this, because this functional form is derived out. It becomes sort of 1, because over here I'm having dx alpha over dx alpha, which gives me 1, and this alpha remains over here. Then you have half times you're taking the derivative of this guy. So when you do the derivative of this guy, this remains as it is, and and this guy becomes 1. So you have x beta minus x naught beta times this derivative. So one of the x's goes away. But then you have to derive the second term. And when you derive the second term, then you are doing x beta over x alpha. So x alpha remains there, but because you have a Kronecker delta between beta and alpha, so alpha changes into beta, and you get the same term. You get the same term twice, and that removes the half. So you get x beta naught dx alpha, which was already there, and then beta, which is summed with this one. And still your summation convention is intact. The next term in the expansion will have 3 powers of x alpha minus x alpha, x beta minus x beta, and x gamma minus x gamma, things like those. And each time when I will derive, I will be left with 2 powers and 3 derivatives. And since I'll be deriving it 3 times, I will collect the same terms 3 times. Because of the summation, everything can be relabeled and you will get the same term 3 times, and you have a 1 over 3 factorial down there. So that removes 3 and you're left with a half. So you are kind of getting a Taylor expansion of the partial derivatives, the correct structure of the Taylor expansion. So you get something like this. And the second derivative. The third derivative, sorry. One derivative matches with the overall derivative you're taking outside, and the others are contracted with these x's. So you get something like this. Now I take this expansion of the partials and put it in 1. And similarly, I take the expansion of G and put it in over here. And then I collect the zeroth order term. So at the zeroth order, so I'm looking at no power of x. By the way, so this is P evaluated at a point. I will have, I must not collect any of this term because they all have powers of x. So I just get this first one. So that has been evaluated at the point. When I put in the same expansion I used for the x new guy from here, I'm putting over here. So I'm expanding these guys. So when I expand this, again, I must not include any x term because I'm keeping the zeroth power. And similarly in G, I must not include any of these guys, just the first where there's no x. So I get G tilde evaluated at a point, and this has to be put equal to eta mu nu. Now this equation I have to solve, or I have to make sure that this is satisfied. So here I start counting. This is just a linear equation. Linear equation where these guys, they are given. This is known, and this is also given. This is just, we know what matrix that is, are given or fixed. Because in the prime coordinate, you know what the metric is, it was given to you, and you can just evaluate at this point, you get a set of numbers. So these are known, these are just set of numbers. And we are looking for, because we are constructing a new coordinate system. So we are completely free to invent a coordinate system. So we are looking for the unknowns, and those coordinate system I am constructing by constructing its Taylor series. So how do you construct the Taylor series? You have to give the Taylor coefficients. So we are looking for the unknowns, which are d x mu dash, these first derivatives. These are the unknowns. So that this equation is solved. And so how do I do it? Well, this is just a counting argument from linear algebra. How many equations I have? You can just look at the right hand side that you have to give certain values to mu nu. So eta mu nu is symmetric. So in n dimensions, how many components it will have? Well, you know that an n by n matrix, if it's symmetric, its components are how many? N into n plus 1 over 2. One can see it in many ways. For example, you can do it this way, that we only need to know the components on the diagonal and above diagonal. So in the first row you need n, and the second you need n minus 1, until at the last place you have just 1. So these are the total number of matrix elements in a symmetric n by independent metric elements in a symmetric n by n matrix. So you know that how to sum this series. This I can write like that. So if I add these two, I'm adding n plus 1 n times. So Sn is n plus 1 over 2, and these are the number of components in a symmetric matrix. So that means I can give these different independent values. So I have this many independent equations available over here. And well, I should not write mu nu here. This should be alpha beta, just for matching the index on both sides. So I can give these independent values to alpha and beta, but I need to remember that I only get these many independent equations. So I have n into n plus 1 over 2 equations in n dimensions. So if you are in 4 dimensions, you have 10 equations. This is also actually equal to the number of components in the metric, because metric is a 4 by 4 symmetric matrix, because it's a symmetric 0-2 tensor in n dimensions. And how many independent variables you have? We have dx mu dash over dx alpha, these kind of things. Mu dash can take n values, and so can alpha independently. So you have to, for example, define, you have to choose it. This is just a number because it's evaluated at a point. You have to give this number. Similarly, for each value of mu dash and each value of alpha, you have a number. So you have n by n unknowns, which you can choose or solve for, whichever way you want to say. So you have n square unknowns, which are n square first partial derivatives at point P. So you have more unknowns than the equations. So unless something is really degenerate over there, you are guaranteed you can easily find a solution. Or I can say one can arrange so that the equation is satisfied. Not only one can do that, actually one can do it in a lot of ways, because you are going to have many free variables, because you have more variables than the relations. So when you will solve the equations, you will left with a huge degeneracy, a huge leftover freedom, and typically you will have we will have freedom to choose, to change them the solution. And what would be the dimension of that space? It's just the difference of the variables and the equations. So n square minus n plus 1 n over 2. So it's n square minus n square plus n, 2n square minus n square minus n. So equal to how many antisymmetric components you have in a n by n matrix. So for n is equal to 4, the degeneracy or the choice is for 6 dimensional, 6 degrees of freedoms. For n is equal to 3, the choice is 3 degrees of freedom. So this is no coincidence that this is the dimension of Lorentz group. And this is the dimension of rotation group. So what really happened over here is that not only you can choose your coordinates, so that at a point you have metric equal to the flat metric, but you can do it in many, many ways. So you have, because why it is there? Because you have chosen the coordinates and you have got the flat form for the metric, but you can linearly transform this metric. If you linearly transform it, your partials, they only linearly transform, and in the new components still satisfy your equations. You remain within that subspace which satisfies this equation. And but once you do the linear transformation, that means you have got a new set of the partials. So you have got a new coordinate system, but the metric did not change. There will be a certain amount of, there is a certain amount of linear symmetry in the form of the metric. We know that this metric this is invariant under SON, and this metric is invariant under SO1 n minus 1. And these are linear transformations. They're all linear transformations. So you can still do linear transformation on the new coordinates you have found. This will not destroy the linearity of the transformation, and the subset of those linear transformation will still leave your metric to the flat form, which is the corresponding symmetry of the metric. So we should have expected that we will have this freedom when we are choosing coordinates. We will have this freedom that locally we can still transform the coordinates without changing the metric. So we have freedom to locally I mean at a point still change. I shouldn't say at a point, at our point which we were choosing, still change the coordinates through a linear transformation that is also a symmetry of the Minkowski or Euclidean metric. And so this freedom is what we encountered. So let me just summarize so far. So far, what we have found. Number one, we can find coordinates where at a point P. Habiba, what are you doing? Habiba, can you remove this, whatever you drew over here? So we can find coordinates where at a point.
सॉरी सर, एक्चुअली वो फोन हैंग हो गया था, उसमें कोई पता नहीं चल रहा था.
नहीं, ये आपने ड्रॉ किया, इसको तो बंद कर देना.
कर दिए.
It's still there. And there's nothing I can do about it.
Sir, it will remove automatically in few minutes.
Okay. So we can find coordinates where at a point P, G mu nu under this coordinate transformation goes to eta mu nu. But this may not be true at other. We haven't proved that it will be true at other points. Since we solved for the Taylor expansion using a fixed, so I should say, may not be true at other points. Because we solved for the Taylor expansion using a fixed G mu nu P. These went into my linear equations which I constructed. This was an input in linear equations, and output was the Taylor coefficients at that point. But if I fix them now, if you fix it, then other numbers, because in my starting coordinate system at other points G mu nu at Q would be different. So at other points those numbers may not solve my linear equations with these fixed dx mu, these fixed partials which I found. So may not be true at other points because using a fixed G mu nu, the resulting, these partials may not solve the equations at other points where G mu nu Q is not equal to G mu nu P. And the second thing we have found that at this point we still have the linear symmetry. We still have the linear symmetry of the flat matrix available. So not only the matrix is flat at one point, but we can change it in many different ways corresponding to Lorentz or rotation symmetry. So this is called local Lorentz or rotation symmetry. So this you have to take. We have kind of proved it. Well, we have actually proved it. And this is given every time, no matter what kind of manifold you are given. You always have this freedom that you can assume that I will be able to find a coordinate system so that at a one point in that coordinate system, not only my matrix will be flat, but also at that point, I will have a full rotation group available to me. I will still be able to make full rotations at that point so that the matrix does not change. So those rotations or those Lorentz transformation which you can make at one point, these are always available and these are called the local Lorentz transformation. or local Lorentz symmetry. So any questions so far? So let us now, let me see what can I do about it. There have to be some, yeah. Okay. Now let us move to next order. And what we get. So now I am keeping terms proportional to 1 power of x. And putting them in this equation. So in the expansion of these partial derivatives over here, I will keep, for example, this term, but I'll multiply it with the term for the other guy when I keep only its first term, because I don't want more than 1 power. And then the other way around. But when I'll do this, I have to still multiply it with the metric, and I'll multiply it with the first term in the expansion of the metric, because I don't want to involve another power of x with the first term over here. But then I will have the option to include the first order terms of the partials, but use the second order term from the metric. So I'll get something like this. Dx alpha, dx gamma. This is the second order term, or term proportional to the x coming from the expansion of the partial. And this was being multiplied by something like that. But I'm dropping these because I'm collecting their coefficients. But then in the expansion of the second term in the equation, I just keep the first order term. And similarly for the metric, the first order term. So everything becomes evaluated at P. Then I'll have the same thing going on for the second thing. Everything is evaluated at P because I'm collecting only the coefficients. And then I'll have these guys first order from these guys and second order from the metric. And this, on the right hand side, I have no term proportional to, because the right hand side is eta mu nu proportional to and x mu. These are just constants, so I get a 0. So again, since every time I just collect the coefficients, every time I get some linear equations. But in these linear equations, these guys they are fixed because I already solved for them using my first the previous order. I found that I need some form for these to solve the first order equation to put the metric equal to 0 equal to the flat metric. So I used up the freedom over here. So these are fixed. I have chosen them. And these are also fixed because these are given to me in the beginning. And we want to put the first derivatives equal to 0. So you can think of it in many ways. Starting from here, these are just some matrices. So I can multiply with the inverse, take them to the other side. So you're solving for these guys. You can bring them on the other side, solving for these guys using these coefficients. And what is the unknown for you? You're putting these equal to 0. You want to, or in other words, you want to put this equal to 0. And these are unknowns for you. We want to put this and solve for unknowns these guys. So you're constructing the Taylor series term by term. Now since the second derivative you can define independently of the first, that's just a definition of the function which you are constructing. So you give the numbers for the coefficients in the second term of the Taylor expansion, or you give the numbers for the derivatives of your appearing in your Taylor series at this point P, and you want to make sure that these which you choose satisfy this equation with this equal to 0. So in other words, you can actually remove this part, put it equal to 0. That's what you want, and the rest of the equation you get this guy equal to 0. This is what you are trying to solve. So now again, you have to do a bit of counting and see, can you do it? So you are solving kind of this kind of equation. These guys are fixed. These guys, but not this. Those you want to solve for. These are also fixed. And there was a term with slight change of it, and that was put equal to 0. And these are the unknowns. So how many unknowns you have? You have if I fix the mu dash, then I can count for a fixed mu dash how many partial derivatives I have. Partial derivatives commute. So partials commute. That means these labels alpha and gamma are symmetric. So that means I can arrange these partials into a symmetric n by n matrix. So again, in 4 dimensions, you have 10 of them, or the previous formula which I had written like this. But I can choose mu dash independently of whatever I'm doing down there. I can choose any of mu dash takes n values. So that means you have n into n over 2, or in 4D you have 40 unknowns. And how many equations you have? That you can count again by, well, I can see it from many ways. For example, I can just look at this guy, because this is I'm trying to put equal to 0. So for each value of mu dash, and gamma, I have one equation. So I can count number of equations from these. But again, I have the same structure. This is a symmetric n by n, and then I have these n indices here. So this is also equal to, number of equations are equal to, again, n into n, or 40 in 4D. So it exactly matches. So if nothing funny going on, like, and you don't want to make anything funny, it's in your hand, you're not drawing lines which go degenerate, you will not encounter any kind of rank reduction in your equations, and you will be able to solve these equations exactly. But just exactly, you don't have any extra freedom. So the first partial derivatives can all be put equal to 0 at the same point, while keeping, we did not disturb, we chose the same first partials. We did not, whatever we got, we didn't use that freedom, while keeping the metric at this point, metric components at this point equal to the flat form. I shouldn't even say flat form, because flat metric can have many different kind of components depending on which coordinates you are. When I say flat form, it's clear what I mean. I mean this form. Cartesian, whatever form the flat metric takes in Cartesian coordinates. Now what happens at the next level? Maybe this pattern keeps going. So at the next level, because the issue is that when I construct this equation, then, well, not this, this is at a point, this equation, then I'm putting the Taylor expansion of the partials. And the Taylor expansion of the partial, when I consider, like, for example, the second 2 powers of x, it has over here. Where is it? Yeah, over here, the equation in the red. When I consider 2 powers of the x, I have 3 derivatives appearing. So that's the main trick, that why these phenomena are appearing. While in the metric, expansion of the metric, when I consider the 2 powers of x, I have the 2 derivatives of the metric. So keeping in this mind, I have to again just collect the terms, and I can just recall from my mind, keeping that thing in over there, that is going to be so I have half 3 derivatives. Dx alpha was already there. I introduce 2 more fiducial um, uh, indices which are being contracting with these kind of things. X sigma minus X sigma naught. But I'm not writing these. Validated a point, then you have the first order term from this derivative, first order term from the metric, and then this same thing happens with the other guy. Dx beta and dx gamma, dx sigma at point P. Then I can also collect first order term from the term multiplying 1x from one partial and term multiplying the x from the other partial. So that will give me something like this. Dx alpha evaluated at P evaluated at P, but I have to leave the metric still to the first order. Then I'll have this kind of term where I will have being one x from the partials. The other partial I keep without an x, but I bring an x from the metric. Sigma. I have to transfer this over here, but I'm not writing. There will be another term exactly like this with some switching, because in the end I'm just going to do some counting. Then I'll have the term where I don't bring any x from the partials. And I bring all the x's. There's some half over here from the metric. Again, I get some linear equation. Some things are fixed over here. So what is fixed? First partial derivatives are fixed. Second are also fixed, because I fixed them in the last order. And these are also fixed, the metric at a point. And the derivatives are also fixed. They're actually 0, so I can drop these kind of terms. So what I'm left with? I'm left with this kind of equation. So let me just write this equation in a very uh, systematic, not in a somewhat schematic way. I have these three partials multiplying with the first order, which are actually fixed. Then I have terms involving the double partials. Then I have the term involving the one partials. And multiplying the second derivative. So now what I want to do, I want to put this equal to 0. Everything over there is known except this guy. These are unknowns. The third derivatives. So I want to choose some third derivatives so that I'm able to put these guys equal to 0. Or in other words, if you want to think it this way, I put this equal to 0, construct this equation and solve it. But can I do it? How many equations I have over here? I have up there G mu dash nu dash. So this is a symmetric n by n. So I have n into n plus 1 over 2. In 4D, I have 10. But then I'm introducing these symmetric indices, which are completely independent of the indices on the G. So they will also be n into n plus 1 over 2. This is the total number. So 10 into 10 in 4D, if I count in 4D, these are 100. 100 equations. And how many unknowns I have? Well, for each mu dash, unknowns are of this form. For each mu dash, you have these symmetric alpha, gamma, and sigma. Three indices which are completely symmetric. You can exchange them with each other and nothing happens because d3 of x mu dash, d3 dx1 dx2 dx3 is equal to d3 dx2 dx1 d3. Doesn't matter. So when you're choosing out of n components, n objects, you're choosing 3 times and you don't care for the order. Well, I don't really want to derive this formula. It will take me way too far from the discussion. But if you have n objects, you draw m times independently. That means I draw once, I put it back, and I draw again. I don't take that, whatever I had drawn, I don't take it out from the next possibilities. And do not count the order of drawing. That means if I draw 1, 2, and 2, or if I draw 2, 1, and 2, I count them as one object. So the formula is this. N plus m minus 1 divided by m factorial. So this was the formula which gave us this thing. For two objects, for two indices, it gave us n into n plus 1 over 2 factorial. For three indices, it gives us, you should prove it. I'll put it in the homework, prove this formula. It will give us this. So for 4D, this gives us what? I guess this gives us 20. So you have 4, 5, 6, 4, 5, 6, 6, you divide by 3, you get a 2. Oh, so these 3 factorials just cancel. So you have 4 into 5, 20. But you can still choose mu dash. So total unknowns are n into n, n plus 1, n plus 2 over 3 factorial. So it's 4 into 20, 80. So you have less unknown and more equations, so you will not be able to solve in general. And in general, you have a deficit of 100 minus 80, 20. So 20 of the second partials will 20 by 20 mean a 20-dimensional subspace in the second partials will not be 0, will not be possible to put to 0. Just wait a second, Asha, I'll get to you. Will not be possible to put to 0 by a change of coordinates. Even at the point P where your G had gone to eta and your first partial had gone to 0. जी बताएं आशा. There are two chats. Equation 1. How are the linears? I mean, let me go back. Equation 1. Equation 1 itself is not a linear. Well, equation 1 itself, it involves the derivatives. So it's a complicated equation involving two functions. But once I start tail expanding it and start collecting terms proportional to x, every time I get something evaluated at a point. So these things are just evaluated at a point, and you have some numbers being multiplied to some unknowns, and they are all linear. Because your unknowns, they are not being squared or anything. Where, how do I see? Where are these equations? Yeah. So like over here, the unknowns are the zeroth order are these. Well, it looks quadratic, but I can, for example, take the inverse from here. and bring it here, then I can think of it as a linear equation. But even as if you look at it as some kind of a quadratic equation, even there you can prove that you can have a solution if the unknowns are equal to the number of equations. But you can simply take an inverse over here and bring it here. Similarly, if I come here, what's the next one? Yeah. So here the unknowns are second derivatives and the others are just numbers. So I can keep multiplying with numbers, but the unknowns, they are linear over here. Similarly, in this last one, the unknowns are these third ones and they are linear. Because all of this, even when things are being multiplied, they are just matrix multiplications. They're not functional multiplications. So when you have these matrix multiplications and the unknowns are just the first order, so then these are just linear equations. So this is what we have concluded, that in 4 dimensions, or in any dimension actually, because this is going to be, you can count, well, anything above 2, you can count that you will not be able to put the second derivative equal to 0. I think in first dimension, 1 dimension, you can do it. And there's no curvature in 1 dimension, no intrinsic curvature. And if we check it, for example, for dimension 2, so what do I get? 2 plus 1, 3, 2 plus 1, 3, 3 into 3, 9. And how many unknowns? 2 plus 1, 3, 1, 2 goes from there, 2 plus 2, 4, and 8. So only one deficit. That means that in 2 dimension, you will not be able to describe, not be able to erase one partial. The rest of them can be put equal to 0. So these will turn out to be, it will turn out, this gives us an idea, you can say, that these partials are capturing the deviation, because that's the first time, depending on going into a special coordinate, that's the first thing which we notice, that's the first thing which becomes non-zero, are capturing the deviations from being truly flat. And we will shortly see that we want to capture it. This is all very coordinate dependent. We want to capture it using a tensor. So we will define a tensor, Riemann tensor, or if you want, Riemann curvature tensor, which will be related to the second partials of the metric. Also, in 4D, it should have 20 components. In 2D, it will only have 1 component. And similarly, you can count in all other dimensions how many it has. And it will turn out that it captures everything there is to know about the curvature. And so in 4 dimensions, you need to specify 20 numbers if you want to specify the curvature at a point completely. Should we discuss a little bit about the Riemann? So Riemann, there's actually a huge amount of things which can be said about the Riemann. I won't have the time to discuss its complete properties because obviously we are limited by time. We are already under extreme amount of pressure because we have to finish some content by the end of the course. So I'll not be able to do complete justice to it, but we will discuss a few things. First of all, let's introduce it. Right now, it's not the most intuitive thing. At least it will not be clear that how it's related to curvature. First of all, how should I define the curvature? But the way I will define it, it will at least, from what we have discussed today, it will at least be clear that it's somehow related to deviations from being flat. And it's a metric. It will have some nice geometric properties. And hopefully next time we will study its properties further, and that will reveal that it's related to our intuitive idea of what curvature should be. So first of all, let's discuss this. Consider a commutator of the covariant derivatives on a vector field. कोई क्वेश्चन है? Okay. So what's the commutator? Is just this. So this is what I want to consider just for now, just for fun. And how will I write it? So we know the formulas. What is this? This is just d mu, d nu, and v alpha, and then minus, you just exchange mu and nu. So we have to write what is this d mu, d nu, v alpha. So this guy, I know whatever this guy is, this is a 1-1 tensor. And I know how the covariant derivative acts on a 1-1 tensor. So what it does, it takes the partial of the 1-1 tensor, whatever the components are. Then it brings in some Christoffels. One time Christoffel for the covariant index, and one times one times the Christoffel for the down index, the one form index, and one time for the vector index. And when it does with the one form index, it does it with a negative sign. So I put mu here, nu here, and a sum index here. So the covariant index I have replaced with the sum, and this guy remains as it is. And the next time I have v alpha, the vector index comes on to the Christoffel, and I have mu, and over here I have a sum index. So let's say sigma v sigma, but the index on the covariant derivative, it just stays there, because this time the Christoffel was for the vector index, like this. And then I have to replace mu with nu and change all the signs. But before we do that, we should probably open this up. So this time I have to just open these guys. So it's a kind of a mess. So once you get this, then you get a Christoffel for this vector. But on that, you have this du mu acting on it. V alpha nu sigma V sigma. It acts on this whole thing. So I'm just directly writing once it acts on the Christoffel, and once the Christoffel comes out and it acts on the vector index. Then I have to consider this term minus gamma lambda mu nu d lambda v alpha and minus gamma lambda mu nu gamma alpha, because the vector index comes on to the Christoffel, lambda sigma v sigma. And then finally it has plus this guy. So I have a product of a bunch of Christoffels and derivatives of Christoffels. Gamma alpha mu sigma d nu v sigma plus gamma alpha mu sigma gamma sigma nu lambda v lambda, and then minus mu exchange with nu. So when I exchange mu with nu, this guy will be cancelled with its counterpart because the partials are commute with each other. So there will be no double partials. Those are gone. Then I will have gamma mu. Let me just write gamma mu d alpha nu sigma. This guy will be there. Then I have this guy nu mu, and then I have this guy mu nu. These guys are, when I'll take their counterpart with mu replaced with nu, they are both there. So their counterparts, this will be counterpart of this and this will be counterpart of that. So they will also cancel. So the first derivative involving v will also be cancelled. Then I have the derivatives of, so I'll have a derivative when I replace this minus d nu gamma alpha mu sigma and then I have these guys mu nu. I will have this mu nu, and in this replaced one I will have nu mu. But mu nu and nu mu, because the Christoffels are symmetric in their lower indices, so this term will not also be there. But I'll have this kind of term. So I will have plus gamma alpha mu sigma gamma sigma alpha mu delta new lambda. Well, I'm keeping what I'm keeping outside. I have been keeping v sigma outside. So let's replace this by lambda. And over here, put a sigma. Because I'll multiply this with v sigma. And then I have the other way, gamma lambda So this guy will also be gone, because when I replace mu nu with nu mu, this will be gone, this guy. But this guy will introduce its counterpart. So I'll have gamma alpha nu lambda gamma lambda nu gets replaced with mu sigma, and this whole thing is being multiplied with v sigma. So I thought we won't be able to do it, but finally we have actually succeeded at giving it a nice form. So that's what is the result of our computation. Now this guy, it has a certain index structure. So I just write it out, and different people write it out in different ways, and picking one particular convention is, I think, is the most common convention. It's a little bit idiotic because you sum this index over here. So mu nu are not being summed. The sigma is being summed with the outside index on the vector. And that sigma I put right here and mu nu here, and there's an upper index alpha. This lambda is summed index. So free index are alpha, mu, nu, and the sigma gets contracted with the outside vector. So I can write it like this. So the alpha index on the vector got translated onto this object, whatever this object is, and it gets multiplied with v sigma. Now you can notice a couple of things. First is the commutator acting on the vector field is not a derivative at all. At all. Because it does not involve any derivative of v. It's just something getting multiplied with v. It's just something, an object, an algebraic object, multiplying v. So this guy can be thought of in its own term. It's just an object which multiplies v. It's not a derivative of v. It does not depend on v. Secondly, this is the left hand side. is a true tensor. Why it's a tensor? Because it's this guy. So you start with this vector v alpha, you take its covariant derivative, it remains a tensor, 1 1 tensor. You take another covariant derivative, it becomes a 1 2 tensor. Same is true for these guys. So you take a difference of two tensors, you still have a tensor. So the left hand side is a tensor, that means right hand side is also a tensor. So this is a tensor equation. But if a tensor is being contracted with a vector, so if this whole thing is a tensor, and this is a tensor, that means it transforms properly, then this thing must also be a tensor. We have done it many times, that there's no other way you can satisfy it. So this also has to be a tensor. This is also sometimes called the quotient theorem. I'm not going to waste time in proving it or arguing it. I think by the amount of things we have worked out, this is quite obvious that if this is not tensor, this is a vector, this transforms properly. If it has some junk in this transformation, it will screw up the whole transformation. The crucial thing is that this is true for all vectors. All vectors. So it's not like that this remains a tensor for a particular vector. It's true for all vectors. So the only way it can be satisfied if this guy is a tensor. So this implies that this object is a tensor. So this tensor, whose definition is given over here. Each piece over here does not look like it's not a tensor at all, actually, because we know that the Christoffels are not tensors. And if we take their partials, well, partial are in any ways turn tensorial things into non-tensorial things. So to start with, it wasn't a tensor. I take a partial, it's a junk. But this particular combination, it has some nice transformation properties that in the end, when you transform everything, everything cancels out properly. And you find out that this particular combination transforms nicely. And so it is a tensor. So this is the Riemann curvature tensor, probably worth writing it again, gamma alpha nu sigma minus rho alpha mu sigma plus gamma alpha assumed index gamma the sum alpha nu this tensor, this is called the Riemann tensor, and we don't know yet, but we should insert over here curvature, Riemann's curvature tensor, or just Riemann tensor. If you notice something over here, each Christoffel has first derivative of G, right? Christoffels were of this form, G inverse dg plus dg plus minus dg, things like this. And I'm taking another derivative. So each piece has at most, well, it may have, because it is acting on this guy as well, it may have the first derivative as well, but at most second derivative of G. So it's constructed out of the second derivatives of G. And we know that the second derivatives cannot be made equal to 0. So in general, it will not be 0. It will be 0 in very special cases. Well, actually, we can show that Riemann is 0. First of all, it's a tensor. If Riemann is 0 in one coordinate system, then it's 0 in all, right? That's the nice thing about tensors. And one can show a space is flat, and I'm taking this definition of flat. A coordinate system exists where metric is takes this form everywhere, not at a point, everywhere. So that's the minimal definition of flatness. We're gonna assume that if you can find such a metric everywhere, then this is just the flat space in hiding. So a space is flat, and this is the definition of flatness when, if and only if Riemann is 0. All components are 0, not even one component should remain. So if part is easy, if only if part is easy, only if means that if g mu nu is eta mu nu, if there exists a coordinate system where g mu nu is just eta mu nu, then all the partials of this metric are 0, so the Riemann is 0. The other one also we will prove is important enough that we should really look at it, but not today. And there are other some things one should notice right away. Well, what can I discuss in the little time we have? I'm gonna stop it at 4:30. Let me just mention a few very easy things to notice. That is anti-symmetric in its these second indices mu and nu, because you can look at this term, you get it by exchange of this mu and nu in this. Similarly, this term you get by exchanging mu and nu of this. Or you could see it from right from the definition. It's the commutator. So commutators are anti-symmetric. And there was something which I wanted to say where I didn't need any much technical detail. Okay, I can say this thing. So suppose you can do this. You can go to a Riemann normal coordinate. Go to Riemann normal coordinates. That would mean that your all the gammas, all the Christoffels are 0. Because remember, we have constructed Riemann normal coordinates where all the first derivatives are 0 at a point, are 0 at a point P. But first derivatives are 0, second derivatives are not 0. That means the partials of these guys, they don't have to be 0. But if I use this property that the first derivatives are 0, then one can compute the R alpha beta mu nu in terms of g's. And if you do this little algebra, bring this down, bring this index down, and you all know that what does it mean. Let's write it this way. Rho sigma mu nu. This is just g rho alpha sigma mu nu. This just turns out to be this. Something like that. I may be missing some symmetry of it, but it doesn't matter. From my memory, I think this is correct. But this is at a point in special coordinates. But you can do it in at any point. You can find new coordinates where this thing will be true at that point. And you can use this to read off more symmetries of this tensor. But there are other ways of reading off its symmetries. We will do the symmetries next time. But what is important is that even in these flattest NF coordinates, you have this formula where the second derivatives are not zero. And you see from here that the curvature will be captured by this tensor through the second derivatives of the metric. I think I'm going to stop here. It's been 2 hours. I need the next lecture to be 2 hour long as well. But can we have it on Friday?
Which time, sir?
Morning?
Yes,
Morning?
yes, sir. Morning possible है, sir.
Morning
About
10 बजे या 11 बजे 10 बजे 10 बजे ठीक है?
नहीं सर 11 o'clock
क्यों 10 बजे क्या है?
सर मेरे बच्चे की ऑनलाइन क्लास होती है
तो वो लेता रहेगा, क्या उसका क्या ताल्लुक है?
सर उसके साथ बैठना पड़ता है उसके
हाँ?
सर उसके साथ बैठना पड़ता है
नहीं, वो खुद भी बैठ सकता है।
सर 11 कर ले ना
11 कर ले तो वो 1 बजे
चले कर
फिर लोगों ने जुम्मा पढ़ने जाना होता ना। 10:30 कर
चल
लेते
ठीक है 10:30 कर रहे हैं ठीक है
हैं। ओके।